But yeah, thanks for having me here. Sorry I couldn't be there in person. And I'm sorry I got the title and the abstract very late, but I think I got all the buzzwords in the title. So if I'm missing a buzzword, you guys can let me know. And let me start by thanking all my students who are working on this or have worked on this, starting with Darn Paul, who switched over from scanning tunneling microscopy to do the first compressive imaging, all the way through all these other PhDs. And my current students working on are Wadey Liu, and then Anthony Gilgem, who just graduated last year and is at the Air Force Research Labs. So yeah, so let me basically start by reviewing the single pixel camera, which I'm sure a lot of people in the audience are familiar with. But the idea is, instead of focusing, an image onto a regular focal plane array detector, CMOS, CCD sort of thing, you focus on a spatial light modulator. And the key here for the rest of this talk then is the spatial light modulator is going to be how we interact with the sensor and sensing the world and the neural network. So it's going to be the front end to a lot of our neural networks. And so, before you do any machine vision tasks, you can use this as an imager. And you could raster scan by having a single micromirror on one at a time, and then the light is directed to a sensor. But that would take, a million measurements if you want a megapixel image, and you get 1/1,000,000 to the light. So instead with compressive sensing, we have these random-ish looking patterns. Now, we know the patterns are not truly random, but they're random white noise-ish in that they're broad in any possible transform. And the really cool thing about compressive imaging, which was invented out there at UCLA and Caltech with, Candes and Terrence Tao and Donahoe independently up at Stanford, and then Romberg came and joined at Candes at Caltech, is that you basically don't need to take 1,000,000 measurements. You need to take far, far fewer measurements. And you have this ill-posed problem, but it's a solvable ill-posed problem. And again, the TI micromirror device is sort of the best possible spatial light modulator. It can flip 30,000 times a second. It now comes up into 8 megapixel arrays, but it's also still not the perfect spatial light modulator. It has a lot of diffraction issues and other optical things like that. But it's the best we have so far. And so again, just to reiterate, you could raster scan, and as you build up the image, you can sort of see the light 1 pixel at a time turn on. And again, if this is 32 by 32, then you're taking 1,000 measurements in raster. In Hadamard, you're doing the same thing, but you're getting 50% of the light because each pattern is 50% black and white. The good news about that then is you get a lot more signal to your detector, but you still need all the patterns to form an image. And so basically at 25%, compressive sensing gives you this type of image, where the Hadamard gives you this type of image, and the raster scan leaves you with that. So compressive imaging is good. You need far fewer measurements. And in terms of machine vision stuff, you might say, well, we have cameras. They're cheap. They're 20 megapixels, 40 megapixels, gigapixel cameras for the government and astronomers sort of thing. But that's only in the visible part of the spectrum. If you go to the shortwave infrared or the midwave infrared, cameras get really expensive. All right, this is just a little plug for anybody who ever has a good idea and it gets rejected by the NSF. Rich and I applied for this grant way back in 2005. And the panel believes the fundamental assumption is flawed in that the proposed random basis set does not result in compression in the usual sense. The second half of that sentence is perfectly correct. The first half, the NSF panel kind of goofed on. So the really cool thing in the infrared is you can buy a single photodiode for $50 from Thor Labs in indium gallium arsenide, where, for a camera like that, for a quarter of a megapixel, you're talking about $25,000 to $50,000. And if you want a megapixel camera, you're talking about $100,000 to $150,000 camera for that type of thing. And the cool thing about the shortwave infrared and the midwave infrared is you can see things that you can't normally see. And so this is black, dark blue oil paint over graphite pencil, and in the visible, you can't see the underlying graphite pencil. But with compressive imaging, you can see this. And this goes way back, but I also like to use this to illustrate. So this is 32 by 32, and as the compression gets about 50%, the image starts to degrade. This is a 256 by 256 image, and you can see that the image really doesn't start to degrade till 2% or so, or 1% measurements. Basically at 5% at 21 compression, you have this really high quality image. And Stan Osher pointed this out to me when I was visiting UCLA in 2012. And that's because basically the sparseness of an image goes as the square root of the number of pixels. So as you go from a 1 megapixel image to a 5 megapixel, or like to 25 megapixel image, the sparsity only increases by 5 instead of by 25. And so that means the larger the image is, up to the point of your detector, you do better. And over here, you have a $50,000 mid-wave infrared camera. And again, we can accomplish the same thing with a single detector and a DMD, and that saves a lot of money. The other thing is, again, this just illustrates the raster scan. As you go higher resolution in the raster scan, you get in the dark noise and the readout noise of your detector. And so that's why having 50% of the mirrors on is really critical. You get this final result. This is 10:1 compression at 256 by 256. Another really cool thing is, Ting Sun was this first student to put a spectrometer behind the digital micromirror device. And again, in terms of machine vision, what this means is you don't just get red, green, blue in terms of the information channels for a neural network or to do analysis on. Here, you're talking about going from 3 channels of color to 500 to 1,000 possible channels of color, depending on your spectrometer. In this example, it's 1,000 different wave bands of less than a nanometer apart. And so this hyperspectral imager just works the same way, but it's like 1,000 single pixel imagers. And this is a comparison to the other technologies, which are raster scan, whisk broom, and so on, up here in the upper right. So one of the things my group does besides scanning tunnel microscopy is we do some optical microscopy. And so in early 2000s, so not that long ago, the way to analyze, for instance, plasmonic nature of particles or analyze a spectrum in a microscope is to find a particle using a regular camera, move it to the center, and then you can take a spectrum like you see down below. If you take a spectrum over the whole image, you get them all combined. And so each particle has its unique resonance, and you want to measure each of those. Nowadays, what people do is they buy a big camera, a nice scientific CMOS camera, and what they do is they spread out the information on the camera in a slightly different way. So they basically have one spatial dimension and one spectral dimension. So you take a slice in X, and then you get all the spectrum in Y on your camera, and then you move this slice through and you build up a hyperspectral image. And this is really great. A lot of people at Rice study plasmonic nanoparticles this way, and they use this in biology as well. But the problem with that is that as you build up this system, you need, a $30,000 spectrometer, a $30,000 camera, and a $20,000 micro-positioning stage to move the sample across that open slit as you take the image. Again, in our system, we take the light off the DMB and we can go to a regular camera, but we can use the other side of the light to go over to basically a $2,500 or $3,000 spectrometer here from Ocean Optics. And this whole system then goes from being $70,000 to about $8,000. And so it opens up a whole bunch of possibilities. And again, doing this in infrared, because you're having a 1D sensor here, is much cheaper than doing it in the if you were to do the previous method in the infrared, where you need a full focal plane array. So that's just some of the motivation, and this just gives you some of the idea of the type of images you get of these plasmonic nanostructures, which people are using them to try to cure cancer, for catalysis, and for other optical basically devices. The other really cool thing many years ago was working with Yin Zhang here in the Applied Math Department and student Chimbo Lee. And because of the universal nature of these measurements, they're broad spectrally, they're broad spatially, the idea is that you can work directly on the compressive measurements. So instead of taking the compressive measurements, reconstructing a hyperspectral cube, then doing dimensional reduction and unmixing to figure out end-member contributions in an image, you can skip all those steps and go directly to this end-member unmixing. And you can even do blind end-member unmixing and other typical techniques like that directly on the compressive measurements. So thinking about using those compressive measurements directly in a neural network to do machine vision tasks it just lends itself naturally from that. Again, just the idea is that because phi, the matrix you're measuring with, is random, white noise-ish, no matter what transform you do on it, this psi just creates a new phi prime that looks very much like phi. So here's, a sinusoid and its Fourier transform in MATLAB. but here's one of our measurement patterns and its Fourier transform. You can see that basically, again, the Fourier transform of white noise is white noise, most wavelet transform of white noise is white noise, and so on. So over many years, we've been working on machine vision tasks with compressive sensing because the overall final reconstruction, especially of compressive hyperspectral video, is really time consuming. We want to know what can we do with a few measurements, 1 to 5, what can we do with 10 to 20 measurements. And one of the new results I'll talk about is this foveation, which can speed up reconstruction time because you're only focused on one area of the image that's of interest to you. And I'll just pause here so that somewhere on YouTube people can pause the video and sort of say, okay, here's all the papers that are relevant to this. And I'm going to focus on sort of the last 3. But the idea is that we have been working in this field for a while. So one of the very first things we did with Rich was the compressive match filter, what we call the smash filter. So here in this system, we had like a toy car, a toy bus, and a toy tank. And we learned, basically we took a bunch of random measurements of them in different positions, and we learned basically which vehicles which after 10 or 20 or 30 measurements. And you can see that as soon as you do 5 or 10 measurements, you can classify very accurately these vehicles, and you can even classify which way they're oriented. But one of the things you'll notice in this plot is that as noise increases, this technique gets worse. So the measurements are universal because they're broad spectrally and they're broad in the Fourier domain, and again, broad in wavelet. But there is a problem with as noise increases, these measurement patterns basically cause issues. And one of the first ideas we had a few years ago on an Air Force project, because we were looking at convolutional neural networks. And if you look at sort of the learned first layer of convolutional networks, you basically see a lot of edge detection filters. Sometimes you see, depending on the data set, a few colors and other things like that. But you see horizontal, vertical, diagonal edges of different frequencies. And we thought, well, we could basically put all of that on the front end of our system and basically use those patterns in the DMD. And the importance here is this 64 by 64 in-gas camera. It takes 1,000 frames a second, so it's kind of a neat little camera. But the problem with it is that it's only 64 by 64 pixels. If you wanted that to be 256 by 256, that's a $50,000 camera. And so if I can take a $2,500 camera and do $50,000 machine vision tasks with it, then that's a great improvement. And so that's what we did. And so we have basically these edge detector patterns that we just run on the DMD. And as you do that, the only difference after you run the first set, you go into a regular convolutional neural network. And in the first layer of the traditional convolutional neural network, there's a max pooling. Well, the sensors on a regular camera aren't designed to do a max pooling. You could build one to do that, but nobody's done that yet. And instead, you're sort of doing an average pooling, or what we call a downsample. So you take an average of the pixel by pixel mapping of these 8 by 8 kernels inside the system. But you can see in theory, it does a very good job on the MEXS stuff. And this is, again, just a theoretical model of replacing the first layer with the downsample instead of a max pool. And we had some test subjects, but this is real hardware. So we actually took toy cars for the Air Force, and we did classification on them, again, in the infrared with a 64 by 64 sensor, and got 98% accuracy with this system. So again, the compressive imaging architecture is really a computational imaging architecture that lends itself to a lot of other stuff. Because like the very next thing you could say is, or what if we want to put learned patterns on the DMD? And I'm going to talk about that, but what I will say next is, one of the other things is other people have worked on this, is you think about how do you train for this? Because in a compressive sensing system, you don't always know how many measurements you're going to be taking to do the classification. Is it going to take 5? Is it going to take 10? Or is it going to take 20? And so the next thing we worked on, and this is with Yibo, who's now at Samsung Research, and this is what we call dynamic rate neural networks. The idea is that we train only on a few sampling rates, so 5 patterns or 10 patterns or 15 patterns on one neural network only. And we zero pad the rest of that vector. So what people were doing before is for every measurement rate, they would build an entire neural network. This way, you only have one single neural network. And even though you don't have every measurement rate in there, you'll see that this works out really well, no matter what the measurement rate is that you input. So you might have this image that's a 1024 by 1024 or a 32 by 32, and then it maps to so many neurons in this system, and you just basically zero pad the measurements. And so we did this first for a single layer hidden neural network, or another name for it's a 2-layer feed forward neural network with 400 neurons. And this was the MEXS data set at 32 by 32. And you can see that this is the single rate, so trained for all 256 measurements, and it classifies really poorly if you give it anything less than 256 measurements. And once you get to about 10 different measurement points, they're not shown on this plot, but where these measurement points are that we trained on are on these dashed lines. And they're the same spot roughly on the 10 points over here and the 10 points over here. You have done enough measurement points to be as accurate as if you had done 50 points in terms of training your neural network. And I want to thank the reviewers. I don't know if any of them are in the audience, but this is one of those things. We did the concept in a single layer, hidden layer neural network, but they were like, no, you should do this on something more complex. And so we did, and we also found a more complex data set, like the fashion MNIST data set. And the idea here is you have a 3-layer convolution neural network for this one, and then we have the coil over here, and we have like a 6-layer convolution neural network. But this idea of dynamic rate training works really well. And again, you can look at it as a function of how it goes as different measurements and as a function of noise. So I didn't highlight that here, but as noise increases, this dynamic rate process actually classifies very well. So we have the DMD as the modulator, and we'd have a way to basically classify for any number of measurements. You take 5 measurements, see if it's classified, take 6 measurements, and so on. The next thing is to improve the patterns and go from basically convolutional filters to learning what pattern you want to put on the DMD. And again, Rich Baranick's group came up with a great method to do that. But the idea is, working in manifold space. And as a physicist and an engineer, I think about manifold space like, there's a camera in that corner of the room and a camera in that corner, another corner of this room, and there's a camera in the parking lot. And you can map all that information it's a megapixel camera to a 1,000,000-dimensional space. And these 2 cameras in this room, those points would be much closer together than the camera in the parking lot for the scene it's seeing in 1,000,000-dimensional space. And so we wanted to basically classify vehicles on an Air Force project. They gave us some of this video, and we played around with different rotations and scalings of the vehicles and all kinds of other stuff. That's all in the paper. But then you have a choice of how do you want to classify, because what type of patterns do you want to learn to put on the DMD? This is before neural networks sort of were all the rage. This is about 5 or 6 years old now. But you could do principal component analysis in real space, but this ignores the differences between the classes. You can do linear discriminant analysis, but it has some real scaling issues. And Rich's group came up with what he calls manifold secant projections, which is to map into this manifold space and then find the secant differences between the different clusters for the different classes. And there's different ways you can do that. The one we did that was most tractable is we're actually still doing principal component analysis, but we're doing it in a manifold space instead of real space. And so say we have 2 vehicles, and we're going to have 3 patterns on the DMD. And we're going to learn these patterns for different rotations and orientations of the vehicle. And these are the different patterns. And you really can't tell the difference between which one's real space and which one's manifold space. But with 3 patterns, you can see that you can't untangle the blue dots and the green dots in these upper plots. And that's real space PCA. But down below here, you can see there's a very nice separation in the clusters of these 2 different vehicles because we're doing the principal component analysis in the manifold space itself. And so, and again, the great thing about this is really robust with noise. Like, not only can I barely tell that that's a vehicle, this can classify it as basically an S10 pickup versus a Tundra pickup, sorts of thing in this test. So with very few measurements, you can do very good classification in high noise environments. Now, one of the things that the problem with that is, though, is we can't still reconstruct an image regularly. So you have to make a choice. I want to run either to acquire video and imaging so that can be reconstructed for a human, or I want to run patterns to classify, but you can't do either. And so one of the things we did come up with was a great way to do compressive video. And this was Rich's postdoc, Ashwin, who's at Carnegie Mellon. And the idea was that when things move, if you try to move to keep up with this swinging metronome, you get a very blurry image. If you use more patterns, you miss the metronome, but you can reconstruct the background. And so the way to solve this and get this great video, and the cool thing also is just like in 2 dimensions, where the sparsity goes as the square root, well, in 3 dimensions, the sparsity goes as the cube root. And so that's why you can get higher compression ratios as you go to higher dimensional data without putting the strain on your sensor. And so this is at 60-to-1 compression in the video. And the trick was we have some low frequency Hadamard patterns and some high frequency looking noise. And the low frequency patterns can be reconstructed to give us the background to do the optical flow calculation. And then that allows us to reconstruct the high speed video. And again, this is not an interpolation. You can see that these are low frequency previews from the Hadamard patterns, but features like the fine lines on the hand and stuff are missing from those. So you're really capturing that information. There's a little dot in the center of this windmill, and that's captured in the high frequency compressive video, but not in the low frequency previews. So this is a great method. And then Ashwin went on to a faculty job. And so then also at UCLA, I ran into this guy passing through named Tom Goldstein, who happened to be a Stan Osher PhD from a few years before. And so when Ashwin left, Rich hired Tom to be the postdoc, and Tom saw what Ashwin was doing, and he thought there must be a better way. And so he invented this transform, like out of the blue, his own sum-to-one transform. And this has this really cool properties that it's not 2-scale, it's multi-scale. So you can get reconstructions at multiple resolutions and still get very high resolution video. And I'm going to talk a little bit later about the heart of our foveation is these stone patterns. So say we want to run stone patterns, so we want to be able to take images and video, but we also want to do machine vision tasks. And so Anthony worked on this, and he said there must be a way to map the stone patterns and the secant patterns together. And he did that using a neural network. So he used a neural network to do a nonlinear transform between these are the actual patterns on the DMD, but these are the patterns that the objects are actually trained and learned and classified on. So this is in no way ever appearing in real space, but you can still map the photon signal from something like the stone pattern to what the secant pattern would have seen and then do the classification. And the really big thing about this is you could do a grayscale pattern on the DMD, even though it's binary, but you trade off multiple cycles, right? So say you want 8 levels of gray, so 3-bit gray, that means your DMD is effectively moving 8 times slower than if it wasn't, than if you're doing binary. And so this doesn't give that trade-off. It's still multiple patterns, but it's only sort of 2.5 or 3 times slower as opposed to 8 times or 16 times slower sort of thing. And so we tested this on the coil data set and a few other things. And this is just the simple neural network that he used. You fully connected layer, sigmoid, fully connected layer, and that's the mapping. So that you start on the optics side, your sensor sees the vehicle plus this pattern, that gets fed into the neural network, and then out comes the classification. And what's really cool about this is it actually, gets to the secant rate in blue, but it actually does better even than secants, because secants, if you notice from their patterns, they're almost all high frequency and very low frequency information. The stone patterns capture low frequency information. And so this S2C2 that we're doing in black, it actually does better than both the stone and the manifold secants independently. So it's kind of a really neat sort of result. And I think I'm doing really well on time, I hope, but I talk pretty fast. But you guys let me know. The next thing I want to talk about is this foveation. So again, reconstructing large images is really expensive. And there have been other papers that work on foveation, but you predefine a region on the DMD and you say, I'm going to do high resolution patterns at the center of the DMD and then low resolution on the outside, like the human eye works or other things like that. Here, this foveation is all done after the fact. So these stone patterns have these really cool upsample, downsample properties because they're not +1, -1, 50% like other Hadamard patterns, but they're really 75-25 in these kernels. And so when you upsample one of these or downsample one of these, you have this feature. So if you downsample like this upper block B, it goes to all white. And if you downsample this one, it goes all black. Like with Hadamard, it wouldn't do that. It would always just sort of be gray, gray, gray. So what we do is we run these full resolution stone patterns on the DMD. Then after the fact, we click a region that we're interested in reconstructing an image or reconstructing video. And the algorithm then downsamples the rest of the information it runs in the reconstruction solution at a much, much lower resolution. And so just like we used a trick from 2D FFT earlier in zero padding to train the neural network, this is an old trick in image compression and data compression called run length encoding. And we basically run length encode these blocks to make all of that algorithm operate much faster than the regular algorithm. And so you can see that you can do different regions here, and you could use these to sum up to a full image. And I'll talk about that in just a second. But this is a great example, especially for hyperspectral imaging, because again, you might have 1,000 channels of color, and then reconstructing the image for all 1,000 of those channels is time consuming. So any speed up you can get is great. And so we went from 16, 17 seconds in this, and this is only actually, we didn't even do the full spectrum here. And we didn't, so this is sort of, if I remember right, 128 by 128 by only 100 channels of color. But you can see that our foveated reconstruction here matches the ground truth. And then where it's outside, the orange square, where it's outside the foveation, you can see, of course, the reconstruction is really rough. But inside, the red and green squares are basically nearly identical to regular reconstruction and the actual ground truth spectrum of this target. So again, one of the really cool ideas, this is what we got from a program manager at the Army, in Army Night Vision, and he was like, oh, well, doesn't that mean that if you run all of these in parallel, you can reconstruct the whole image faster? And we're like, yes, it does. And so you can see that basically, if you reconstruct different parts of this image on a GPU in parallel, then the total reconstruction time, it goes down from 16, 17 seconds to only 6 seconds, but not just for the foveated region, but for the full image. And that's not a really great speed up, but it also gave Anthony this idea that there are some neural network solvers out there for compressive imaging, but all of them have a scaling issue, that the bigger the image gets, they don't work very well, or almost all of them, I would say. So this one, it scales fairly well to high images, but it has a very slow reconstruction speed. Rich and his group came up with this deep inverse that actually has a great reconstruction speed, but scales very badly as images go from 128 to 256 to 512 by 512 and so on. And so Anthony wrote his own neural network solver. And so this is for a regular image, 128 by 128. And this is the details for the neural network people. But this is the regular PDHG L1 solver. And for one grayscale slice, it takes, 1/5 of a second. For here, you're down to a little over 1/10 of a second. So it's much faster. And what's really cool about neural network solvers for hyperspectral stuff is even though you're looking at 64 different color channels now in these two images, it doesn't scale like 64 times faster. It's 64 times slower. It's only, 4 times slower in neural network. And whereas the full reconstruction for all these slices is, it's half of 64, a little less, like a third of 64. So it's 27 seconds for these images versus the neural network solver. But again, this is a great solver, but it doesn't scale well to larger spatial resolutions. But this does give you an example. And again, for all of these things, it's really important to look at the point-by-point spectra comparison, because even though things might look good in an RGB representation of a hyperspectral image, it's the details in the spectrum. But again, you can see on the left is the L1 solver, and on the right is the neural network solver. And again, this is a 320x speed up for all 100 channels compared to the PDHG solver. We did it in basically, that number you're looking there, say 60 frames a second. So you don't have to worry about even having a video solver. You can do individual images at 60 frames a second reconstruction. And then Anthony took this and he wrote one of these basically for foveation as well. And so this is an image of a bear, and this is, the ground truth, and this is lower downsample of the full image from the Google Open Image Database. And this is the foveated network reconstruction, giving you an SSIM of 0.58 and 0.56. And the PDHG is 0.57, which this is clearly a rounding thing. I don't think we're really truly better, but here, this is probably more realistic. This is 0.62 for the millipede on that thing. But the cool thing is you can basically now do this reconstruction, 13 times faster for every spectral channel that you care about in your image. And actually, that's it. So you guys will have a much longer break next time. I do have some other stuff I can talk about, but I would like it not recorded and displayed on the web.